All right, welcome to the CMU workshop in cryptography. I'm just really excited to see all of you today. And first, I want to just thank the speakers. Like, I know that some of them have like the 4 a.m. Flights, and some of them have like multi-hop because I mean, Pittsburgh is really sometimes it can get hard to commute from like all places in the US. So thank you for making it, and thanks for to all the like listeners. Okay, so what's this workshop about? Basically, the story goes as follows. Like back 6 months ago, when we were, there was this NSF announcement came that they're going to host like a PI meeting in cryptography in like security-related areas. That was 6 months ago, and Elaine and I were talking, and we were thinking, oh, we should like seize this opportunity to maybe organize a workshop. That time, it was not very, thought through. It was just like no grand ambitions, but. When we started like reflecting on what's going on and like looking at like some of the recent papers, there's this clearly an exciting theme that is emerging out. So on one hand, in cryptography, we have like seen a lot of progress in like many years with our theoretical ideas, but currently we're in a phase where on one hand, we are transitioning to practice on many of the primitives, right? And on the other hand, we're just establishing just mind-blowing feasibility results like year after year. And to me, what stands out, first of all, it's a big victory of theoretical computer science. I think like it's very cool to see TCS tools being used, like, and they are one of the main primary driving factors in all this like improvements over the, like, it's really nice to see all of that. But to me, what like really stands out is like their last several years, we've been seeing interesting, exciting cross-pollination of ideas with coding theory, quantum, and amazing set of things. And also people are beginning to open up to new mathematical structures and leveraging new hardness assumptions to get like even more mileage into things, like things which were not feasible before. Currently, like we are kind of making strides into this and connecting ourselves deeply to the underlying mathematics of cryptography, right? This was not, I mean, for a long time, we were very traditional about assumptions. So this workshop is not about any individual primitive. It's not about FHE or CK proofs. What it's about is just celebrating connections to mathematics, TCS, and hardness assumptions, which is a primary facet of like pillar on which all of cryptography stands. So this will be like just a workshop of cool ideas. So feel free to just go wild and like ask questions. The format of this workshop is really simple. Like there'll be 7 speakers, all of them superstars, and they'll be talking about like first few talks will be about like connections to TCS more or less. And the last 4 talks would be roughly about like new mathematical structures and hardness, things like this. So this is how the talk is structured. We will also have a talk on average case complexity, a tutorial on like how to analyze new assumptions from using sum of squares tools. So this is really the agenda, and each talk is about 40 minutes, which means maybe the talk is could go on for 38 minutes or so, and maybe I will have 2 minutes of questions, which is small, but like I'm just, all of the speakers, they just had one day, and I'm just happy that they are able to pack it up in this small time. So yeah, that's the thing. And then we will have breaks in between, and in which case we can ask questions and like find more time to interact. Yeah, and that's that. So with this, I want to invite first Daniel Wichs, and he's going to talk about I'm actually not going to spill it, so I'll just let Daniel talk about this amazing PIR, which, I mean, the server does not even need to look at the entire database in order to answer, like look up really what an index is. So what a database entry is. So yeah, I'm going to just pass it on to Daniel, and yeah, let's begin.
Thank you so much, Aish, for the introduction, and thank you to the organizers. It's a great workshop. I'm excited. So I'm going to be telling you about double efficient private information retrieval and fully homomorphic RAM computation. This is a joint work with Wichs and Ethan Muck. And I'll explain what these terms are a little bit later in the talk. But before I do, let me kind of start with a high-level motivating example that I think illustrates what this works. And the example comes from just simple Google search, something we do all the time. So if some user wants to ask a query to Google, for example, is wondering if drinking a cup of coffee might be too many. This could be based on a true story. So, you send the query to Google and Google gives back some search results. And so this is something we do all the time, but I think increasingly people are becoming aware of the privacy issues that come along with this. Google's essentially, by seeing all of our queries, all of our internet searches, Google is learning a lot about private lives. It's not just Google, it's essentially all of the cloud service provider, all of the internet tools we're using in our daily lives. And so what we would like to do is to have a private Google search. So here, the hope would be that the user can somehow encrypt their query with a secret key that only the user knows. And then she would send this encrypted query over to Google. And Google doesn't have the key to decrypt it. So Google has no idea what's inside this encrypted query, what the query itself is. But nevertheless, Google can somehow compute the search results under encryption and give back the encrypted search results back to the user. Okay, so that's the hope. And amazingly, we actually have this really powerful tool called fully homomorphic encryption that exactly solves this problem. You can do arbitrary computations over encrypted data without knowing what the underlying data is and come up with the encrypted answer. This is a breakthrough result from 2008 and so on. There's been a lot of work, both in theory, understanding what assumptions we can build this under, and in practice, actually building schemes that you can use at least some special cases. But I claim there's a pretty major caveat, especially when it comes to an application like Google search. And the major caveat is if you wanted to use fully homomorphic encryption or FHE to do a Google search, Google would need to read the entire content of the internet to answer every single search query. Okay, and presumably that's not what happens now. That's not what Google's doing now. Google has built up some clever index of the internet, and when it gets a search query, it just looks up a few locations in an index, doesn't scan through the entire content of the internet. But with FHE, it would need to scan through the entire content. And this is not just like a small accident of the current scheme, it's really the basis of how these schemes work because they operate in the circuit model. Essentially, all that fully homomorphic encryption does, I mean, I say all, it's an amazing thing that can be done, but all it does is you can take two encrypted bits and compute an encrypted NAND of the bits. And because NAND gates are complete, you can now compute any circuit. Okay, and so it really is tied to the circuit model of computation. The circuit model of computation, circuit has to read all the data that it ever operates on. You cannot just access some small subset of locations. Okay, so this major caveat is really inherently tied to the current kind of template of FHE. And so the high-level goal of this work, what we're achieving here, is to essentially port FHE, fully homomorphic encryption, into the RAM model, the random access machine model of computation. So you can do computations that don't read all of the data, just read some subsets of the data. And I'll tell you exactly what it means later on, but what it would mean in the context of Google search is that Google would pre-process the internet content, just like it does now, would build some sort of an index, but it would build a special index that's aimed for encrypted search. It would build some sort of special, different looking index, some sort of data structure. And using this index, it could take any encrypted search query and process it, give you back the response by only making a small number of lookups into this special index. And the kind of interesting thing or the difficulty here is it sees what locations in the index it's looking at, in this special index it's looking at, right? It's looking at them, it knows it's looking at them. But it doesn't know what the underlying data that these locations correspond to are. If it did, it would learn something about what the user is searching. So even though it knows where in the index it's looking, that doesn't reveal anything about the query. Okay, so that's the goal. Okay, so now we're gonna kind of actually explain things in a little more detail and get more technical. And actually, for most of the talk, I'm gonna do a bait and switch. And instead of talking about polymorphic encryption, I'm going to talk about a restricted special case called private information retrieval. You can think of this as just doing a single encrypted memory lookup. There's an encrypted index I, and you're supposed to look up the ith location in memory without learning anything about the index I. And this is really the heart of the matter. If you can do these memory lookups, you've gone a large part of the way there. And we'll show actually with the scheme we construct, you can actually fairly easily then convert it into doing general computation into fully homomorphic. This is not generic. It's actually still an open problem. If you can generically go from the top to the bottom, we don't know how to do that, but for the specific scheme, we can.
Can you show that, maybe a slight strengthening of doubly efficient DEPIR? Is there a generic statement kind of hiding in here? Maybe not like top to bottom, but like a plus to bottom.
I can think of some, but they wouldn't be beautiful. Like you would have to kind of hack at it to make it work.
Okay.
Yeah. Good. Yeah, that's a good question. Maybe. We do have a result if you have a strong enough, if you have virtual black box obfuscation, you can actually go top to bottom, but without like really heavy tool heuristic. Okay, so let me start with the private information retrieval. So as I said before, this is a problem where the user just has an index I, and the server has some big database or memory of size n, and the user just wants to retrieve the ith location in this database without revealing the index I to the server. So for example, you can think of the server as Netflix, and the user wants to retrieve the ith movie, like download a movie from Netflix without Netflix knowing which movie the user is downloading. So there's a trivial solution, which is the server just sends the entire database to the user and says, get your index I. But that's really inefficient. We want to do better. And it turns out that this problem has been studied quite extensively for close to 30 years. And we have solutions under many crypto assumptions. We know how to do this with really small communication, just polylog in the database. Okay, so that's great. But there's a caveat. And the caveat is the communication is small, but the computation is large. In order to do this, to run this protocol where the server retrieves the ith location of the database, the server has to read the entire database during the protocol. And actually, if you think about it a little bit, this is inherent. You need to do this because if the server didn't read some location of the database during the protocol, it would learn that the user is not retrieving that location, which would violate privacy. Okay, so this is actually, you do need to do this, but we want to get around this anyway. Okay, so how can we do that? Well, we're going to change the model. We're gonna change things up a little bit. And the main change is that we're going to allow some pre-processing. We're going to allow the server to take this database and pre-process it into some data structure. I'll put a little tilde over it to show the pre-processed database. This will happen before any client comes. This happens in an offline phase. It's only done once, and afterwards, the server can run protocols with many clients that want to retrieve various locations. This is just a one-time pre-processing phase, and it's ideally it should be a completely deterministic process. That's what we'll achieve. So there's no randomness here. There's no secrecy. There's no just a completely deterministic function the server applies. Now this pre-processing at least has to read the entire database, so it'll run in time at least linear, and then can run in even slightly pseudo. And then once this pre-processing is done, any client can come, any user can come and run a protocol to retrieve the ith location of the database without revealing the index I, where during the protocol, first of all, we want small communication, like polylogarithmic, but also small computation. The server should only run in sublinear time, which means it only touches some small number of locations in this pre-processed data structure, this pre-processed database. And so this is the problem, and maybe like to understand what the difficulty is, kind of similar to what we talked about with FHE, or with the the server sees which location of this data structure it touches. And because it's only a small number of locations, information theoretically, they only contain information about some small subset of the bits of the database. So if the server had like unlimited time, it could figure out which location of the database these guys correspond and learn something about the query. But we want to ensure that if the server is efficient, it cannot learn this. So we need some computational assumption about these locations. But this kind of doesn't look like any of the computational assumptions we have in crypto. It's not clear how factoring would, or hardness of factoring would give you this type of data structure. And I think that's like some of the difficulty when you start thinking about this. Okay, so let me just say a little bit about the prior work of this problem. So the idea of this question was introduced in work of Weimel, Isha, and Malkin in 2000. And they give some positive results for the case of multiple servers, but for this case of single server that we're talking about here, they mainly ask the question, is this even possible? And I think for a long time, it was really unclear. In fact, some time ago, I tried very hard to prove that this is impossible. I failed, but yeah, I really didn't know what your answer would be.
Unfortunately, we failed.
And yeah, so and so for a long time, really, it was very unclear which way the answer should go. And then in 2017, there was a sequence of works that really gave the first evidence that the answer should be positive, that this should be possible. But they didn't quite solve the problem. They gave a heuristic construction and not quite of the version of doubly efficient peer that I'm talking about, but a very relaxed version. So what is the relaxation? They had a keyed doubly efficient peer. The database isn't just preprocessed deterministically by the server. It's preprocessed using secret randomness. So it's to be done by some trusted party that preprocesses the database, gives the data structure to the server, and gives some public key to the users that they can use to run these queries. So it was a relaxed version. Still could be very, very useful in most applications. Maybe this would be good enough. But in addition to that, the security was not under kind of standard assumptions we have. They need to make new assumptions, some sort of a new assumption on permuted Reed-Muller codes, plus an additional heuristic use of obfuscation, which is a powerful primitive that we don't fully understand it. Okay. And so in this work, in this result, we were able to construct the standard version of doubly efficient peer, where the server just preprocesses the database deterministically from a standard assumption, like something called the ring learning with errors assumption. This is a nice assumption. It's been studied quite extensively. It's hard as finding approximate shortest vectors in ideal lattices. In the worst case, so we have some good theoretical understanding of this assumption. And it's well studied. In fact, it's the basis of the new NIST standards for post-quantum secure public encryption. There are some other assumptions you can exchange this for, like approximate GCD, ntrue, or rank, or module LWE. I think ring LWE is the nicest of these assumptions. I'll just the scheme actually has a really nice format. It has the optimal two rounds. So like after that base is preprocessed, the client just comes, sends a query, and gets a response in one side location of the database. And in fact, you can even have a version where all the client does is just send the indices in the data structure that the server should look at and set back. So the server just sends a subset of indices. The client just sends a subset of indices. The server just looked at those indices in the data structure, sets them back.
It's without loss of generality.
If the lookups are kind of static based on the query, if they depend on the database, on the data structure, then it might not be. So it's not fully generic. Yeah.
Right.
Okay, and in terms of parameters, for any constant epsilon and a database of size n, the preprocessing runtime is just slightly superlinear of n to the 1 plus epsilon, and the protocol runtime and the server computation, number of indices the server looks at, is just polylog n. So in terms of asymptotics, this looks great. In terms of real parameters, it's terrible. It's pretty much at this point unusable. So there's a lot of work to be done to actually make this. But in theory, it looks nice. I just want to mention that there are some alternative steps to doubly efficient peer that you could imagine using, and that a lot of people, especially this room, have studied, namely oblivious RAM and here with client preprocessing. These are much more practical than the scheme I'm going to talk about. So actually, in practice, probably these are the more likely to be used. But the main difference between these primitives, which I'm not going to say what they are in detail, but the main difference between them and what I'm talking about here is that in these primitives, you need some separate preprocessing for each user that joins the system and wants to make queries on the database. So for each user, you need to somehow preprocess the database and give them some secret state that the user keeps. In ORAM, actually, also the server storage grows with the number of users. So for each user, you have to have a different preprocessed version of the database. In pure client preprocessing, it's not the case. The server just stores the database as is, but each client has some sort of a different hit that you need to spend a lot of time generating. Okay, and the cost of this big preprocessing is only amortized if a user stays for a long time and makes a lot of queries to the database. Otherwise, you shouldn't have done this. Okay, so that's the main difference. So now let's talk about how to construct doubly efficient here. And I'm going to give you a high-level template, and maybe the super high-level story is like, don't overthink it. Just do the simplest thing, do the most basic thing, and hope it works out. And sometimes you get lucky and it works out. So here's the template. Let's first start with a basic private information retrieval scheme that doesn't have preprocessing and is not efficient on the server side. The server reads the entire database, but has small communication. So without loss of generality, the scheme looks something like this. The client takes the index, uses it to create a query. I'll call that alpha. The server applies some function on this query alpha, so some function FDB that depends on the database, and replies with some answer beta. And from this beta, the client somehow figures out the index of the database. Okay, so we have a lot of schemes like this that do this. And then take a scheme like this and figure out how to preprocess the database to make it real efficient to run this function FDB without reading the entire thing. Just by come up with a specialized data structure that lets you compute this function by just looking at a few entries of the data structure. So that seems like really optimistic, but why should you hope for this to be the case? Like, this function does some complicated crypto operations. Why should you expect this to be? Why should you expect to be able to preprocess this? And in fact, I think for most schemes, you shouldn't. This is going to be a complicated function. It's unlikely that you could do it. But we're going to come to try to look at a scheme that has some nicer structure that will allow us to do this. And the nicer structure is that the client query, alpha, actually consists of some small number of ring elements over some ring R. And the server response is just some low-degree multivariate polynomial over these ring elements. And if you can get a scheme that looks like this, then you can use a really cool results from the algorithms literature, a result by Kedlaya and Umans, which shows that we can pre-process multivariate polynomials over certain rings R into a data structure that then lets us evaluate the polynomial very quickly without reading the entire polynomial. Okay. Now, this result comes from algorithm, and there's a lot of restrictions about what kind of polynomials you can preprocess with parameters. And then here, there's cryptography that has a lot of restrictions about what kind of schemes you can get and what kind of polynomials you get from the basic peer scheme. And again, a priori, you should not expect that these would match up, but sometimes you get lucky. And here we just got lucky. And it turns out that the parameters that you get from the algorithms really match what you need to do the cryptography. Okay, so let me start by saying just a little bit about this result of Kedlaya and Umans, and then I'll tell you about how to construct this basic peer where the server computation is a polynomial. So here's the result they showed. They showed that you can take a multivariate m-variate polynomial over some specific rings R, where the individual degree in each variable is less than d, and pre-process it into a data structure such that later you can really quickly evaluate this polynomial on any input by looking up only a small number of locations in the data structure. And I'll tell you the parameters in a second, but maybe first think there's a trivial algorithm you could do, which is just the data structure, which just lists all evaluations of the polynomial and all possible inputs. And then you can easily, like when you get an input, you can just look up the evaluation. So the problem, we cannot do that because we're going to use rings that are super polynomial size, that are big, exponential size, security parameters. So we cannot just like enumerate all the elements of the ring. So Kedlaya and Umans showed how to do that even for very large rings. You don't have to, you can do something clever when the ring is large. And I'll show you the parameters. So just to see this, the number of coefficients in such a polynomial is just the degree to the m power, where m is the number of variables. So that's the size, just the description size of the polynomial. And here they have a complicated expression, so maybe don't parse it just yet, but the preprocessing time is something that depends on n plus some other factors. And the evaluation time, this expression, maybe don't parse it just yet, we'll have a lot of freedom how to choose d and m, the degree and the number of variables, subject to d to the m being the database size. When we do this, that's what it will be. And so we're going to choose d to be a big polylog, the degree to be a big polylog, and the number of variables accordingly to be log base d of n. The ring size is going to be something like 2 to the Turing parameter of polylog n. And if you just plug that in, essentially this becomes n to the 1 plus epsilon, and the preprocessing time becomes n to the 1 plus epsilon, the evaluation. Right. Notice that the ring size here is super polynomial, so you cannot just like enumerate all the values. Okay. Now this doesn't work for all rings, but it turns out to work for rings like ZQ or even polynomial rings, multivariate polynomial rings, and so on. So large class of useful rings that you might want. And I'm not going to show you how to do this, but I'll tell you a high-level idea. Maybe at least if the ring is CQ. So the high-level idea, yeah.
Which rings does it not work?
So one thing I would really like for this to work over is a ring of matrices.
But that's not commutative.
It's not commutative. Yeah.
Rings.
I don't know if it works for all commutative rings.
Once I think. Yeah, but
I think they explicitly talk about these rings, but yeah.
What would you get from these over rings?
Oh, you would do it from standard LWA. That's if you could do it. Yeah, but right. So yeah, they're not commutative. And actually, like essentially the way Kedlaya and Umans works is that you can reduce polynomial evaluation over any of these rings to just polynomial evaluation over the integers. And that's the first step. They just say somehow convert this into evaluation over the integers, where the size of the integers is somehow bounded depending on the ring size you start with, but large. And then use the Chinese remainder theorem to convert evaluation over integers to evaluation over many small primes. Okay, so if you can evaluate the polynomial over many small primes, the product of the primes is bigger than the integer value you get, then you can reconstruct the value over the integers. Now, if the primes are small enough, then now you can just do the trivial thing where you evaluate over all the possible primes, where you just build a table of all possible evaluations. If they're not small enough, you can recurse. You can do this again, think of evaluating that smaller prime as evaluation over the integers, convert it into another product of integers, and eventually the primes will get small enough that you can. And actually, for our case, for these parameters, you need one level of recursion. You need to recurse once. Okay, so that's the high-level idea of how this works. It's a really clever idea, but it's not complicated. Very easy. You just give the truth table. And see, our number of variables is pretty small. It's less than log n. Actually, it's log n over log n, something like that. So, you can just give the truth.
Prime is polylog n.
Yeah. Say it again. The recursion definitely has a lot of overheads. You increase the number of primes you have to evaluate it over. So, yeah. The constants here are kind of are large. No, that's okay. Just the size. You have to worry about the size of the integers which corresponds to the size of the primes, and they're big enough that you do need to do this recursion. So, yeah.
mean, you could pick the ring to be not CQ or prime Q, but rather Z, Q1, Q2, then small product, small ring. I mean,
That's right. You still need to do the recursion though, so you still need to.
Yeah.
So yeah. We talked about all these tricks, and yeah. So right, the basic scheme is really terrible. You can try to optimize it. You get something just terrible, or so you know maybe that's yeah. Okay. So that's pre-processing. But now our goal is to construct a basic two-round peer protocol where the server's computation is just some polynomial evaluation. And we're going to do that using some sort of somewhat homomorphic encryption, essentially a homomorphic encryption scheme that allows you to just evaluate low-degree polynomials for encrypted data. Okay, and so the idea is the client has some index I, but we're first going to just think of it. We're just going to write this index in base D, where D is some prime, and just these values will be the digits of the index I1 up to IN. And if you now think of the computation that takes the index I and returns the ith entry of the database, you can think of that as a degree in a polynomial in these m variables of individual degree. You can interpolate a polynomial. There's n coefficients, and you can interpolate a polynomial of this type that computes this function. So there's a polynomial, you can efficiently define this polynomial. So now, at least the plain text computation that the server is doing needs to do is a polynomial evaluation. And so now the idea is to use encryption. We're going to encrypt each of these indices under some secret key that the client chooses, that the user chooses.
Right, something like that, because
the total degrees D times M of the. So the individual degrees D and the total degrees D. Yeah.
The other way around, right? The individual degrees M and the total degrees D times M. It's like each variable you have to, is it equal to a particular index? Maybe.
The degree is, individual degree is, well, it's D, as such it's the,
Base D, okay, sorry.
Yeah.
You're right. Sorry.
Yeah, I mean, there are D to them coefficients of the polynomial. Okay, so, right, so we need to evaluate to homomorphically compute this function over encrypted digits of the index. So the client is going to encrypt the digits, send the ciphertext to the server, and the server is homomorphically evaluating this function over the encrypted data. So operating on the ciphertext in such a way that the ciphertext it gets, beta, will be an encryption of the output of the function, just the ith location of the database. Okay. So now, if we have this, can we just apply the Kedlaya and Umans preprocessing on the server's computation? I mean, the server is homomorphically evaluating polynomial. We know how to preprocess polynomial. Looks promising, but no, not quite. We're not there yet. The server is not just evaluating the polynomial. It's doing the homomorphic evaluation of the polynomial on encrypted data. So it's taking ciphertext and doing some operation on the ciphertext that results in the output ciphertext evaluating the output. But who knows what this computation of the encrypted data is, right? In fact, if you look at modern fully homomorphic encryption schemes, this will be something pretty complicated. It won't be a polynomial. But it turns out that we can come up, or we can find encryption schemes where if you want to evaluate polynomials over encrypted data, low-degree polynomials, then all you have to do is essentially just evaluate the same low-degree polynomial over the ciphertext. So we call this algebraic somewhat homomorphic encryption scheme. It's an encryption scheme where you encrypt messages over some ring ZD into some ciphertext over some other ring R. And if you want to add the messages, you just add the ciphertext. So if you add the ciphertext, you get a sum, it decrypts to this, it's an encryption of the sum of the messages. If you multiply the ciphertext, it's an encryption of the product. There's some noise term that grows when you do too many operations, so you can only do this some limited number of times. That's why you can only do low degree polynomials. Okay. And so if you have that, then if you want to evaluate a polynomial over the set, then if you want to evaluate a polynomial over the plain text, all you need to do is just evaluate that same polynomial over the ciphertext. Skip this. And it turns out that if you look at modern fully homomorphic encryption schemes, they don't have this format. But if you look under the hood, they're based on schemes like some partially homomorphic schemes that can evaluate functions, but that exactly do this. So kind of modern versions don't, but if you look back in the literature at like a simpler homomorphic encryption scheme, they actually do have this format. And you can get a nice scheme like that from the ring LW assumption, some other assumptions as well. Okay, so with this type of scheme, with this algebraic somewhat homomorphic encryption, the service computation, which is supposed to be homomorphic evaluating the function, this function of encrypted data, is itself a polynomial over the ciphertext. And so now we take this polynomial over this ring, whatever the ring of the ciphertext is, and pre-process it with the Kedlaya and Umans. And it turns out this ring is itself some multivariate polynomial ring. You don't run like Kedlaya and Umans works for those rings. Yeah, the polynomial doesn't depend at all. It's doesn't depend at all on the decrypt on the secret. It's really this polynomial, which is just the polynomial value on the plaintext data, which doesn't depend on the key, lifted to the ring R, and the ring R doesn't depend on the key either. So none of this depends on the secret key or the particular client you're going to talk to. You pre-process it once, there's one fixed ring, and then any client can come and pick its own secret. Don't need to know it. Okay, so that is it. That's the basic. That's the main idea. If you set the parameters correctly, you can make this work. I want to talk a little about updates. So suppose that you do this, you pre-process this database, and now you want to change one bit of the database. You want to update some bit. Can you correspondingly update the data structure without recomputing it fresh? Because computing this data structure takes super linear time. It's quite expensive. Can you handle updates efficiently in sublinear time? And if you think about the basic scheme, absolutely not. If you change one bit of the database, it affects every single bit of the data structure. There's no nice way to update it. But it turns out that there's actually a fairly generic idea to take any double efficient peer with like a relatively small pre-processing time, like we have, and the 1 plus epsilon, and convert it into an updatable scheme where the updates take O into the epsilon. And I'm not going to have time to tell you how to do this, but for those who know, this follows the ideas of hierarchical RAM. You somehow have a hierarchy of data structures of increasing size. Whenever you write some data, you put it in a very small data structure. And then when you've written enough data after enough steps, you kind of combine, you do a fresh pre-processing over just the data you've written. And so you kind of move them into a bigger level of the hierarchy. So that's probably too high level, but if you know hierarchical RAM, hopefully makes sense.
So one thing that, the going from DEPIR to FHE, RAM-FHE, right? The writing is a problem.
Yeah.
You're saying no, writing generically.
Well, this allows you to do that.
Right.
Yeah, this allows you to do that.
Can you say?
Yeah. So perfect. So now we're going to talk about polymorphic encryption, and I don't think I'll have time to show you everything, but hopefully we'll at least say what the promise. So first, let's just start with the prompt statement of what I want to do here. So here we have a client with some input X. I want to do the generic problem. The server has some input Y. And this client wants to learn this function f of xy without revealing the secret input X to the server. So this could be just a generalization of private information retrieval. The X could be the index in the database, the Y could be the database, and the computation just outputs the correct bit of the database. But it could be something much more general, like Google search, right? X could be the Google query, Y could be the Google's index, and this function just computes the search results. Okay, so there's always a trivial solution. Just the server sends Y to the client and says compute yourself. But there's two reasons why you might not want this. So one is like in the case of Google search or private information retrieval, the Y is really big. You don't want to pay the communication of sending it to the client. But actually, even in scenarios where Y is small or empty, this is interesting because maybe F is very expensive. The client doesn't want to do the work of computing this function over its own data. It's too expensive. It wants to outsource that work to the server. So here we're hoping that the server does all the work and the client does very well. Okay, and this is exactly the problem that fully homomorphic encryption solves. Here, the solution template is the client encrypts its input X, sends it to the server. The server does represents this function F with Y hard-coded as a circuit and evaluates the circuit over the encrypted data. Runs some homomorphic evaluation that produces a ciphertext which outputs which is an encryption of the output of the circuit. So the ciphertext decrypts to C of X, which is just F of X. Okay, that's the template. That's exactly the problem that fully homomorphic encryption solves. And the client runtime and communication are great. The best you could hope for, just linear in the input size and output size of the function. But the server runtime is proportional to the circuit size. And like we said before, for many computations, like just memory lookup or Google search, the circuit size is much, much bigger than the RAM runtime of the computation. So this is what we'd like to get around. But we know how to do this, how to build this type of fully homomorphic encryption where you get the circuit size runtime from just the learning with errors assumption. Okay, plus circular security. You want to do unlimited computation. Think of it as a minor caveat. Okay, so the goal of RAM fully homomorphic encryption of our work, which has to convert this to the RAM setting, is essentially to get everything the same, but not for circuits, but rather for RAM programs, and have the server pay in the RAM runtime of the computation. If the computation takes T steps on a RAM machine, the server's runtime to value encrypted data should be just over. So unfortunately, this is impossible for the same reason here was impossible, because if the computation only reads some small number of locations of Y, then by seeing which locations it's reading, the server learns something about the computation. So the only way to make this work, just like with Doubly is that there's to be a pre-processing step where the server takes its input Y and pre-processes it some data structure. And ideally, the pre-processing time would be just linear in the database. And essentially, we achieve that with just some 1 plus epsilon. We achieve close to that. Yep. 1 plus epsilon and polylog vectors everywhere. Okay, let me maybe skip this in interest of times. Kind of want to answer the notes question. So yeah, there's a couple of challenges. In general, we want to handle programs that have random access both to the client's encrypted input X and the server's input Y. But even let's focus on the simpler case where you don't have writes, you have read-only access to Y. So let's even ignore the question of updates. The computation, maybe for Google search, that's good enough. Read-only access to the index. And there's access may be small, so there's no random access to X. You just have to scan all of X. Okay, so this might be good enough for Google search. Well, our work does the general case, but let's just start with this. Okay, and so you can take this RAM computation and think of it as some sequence of like CPU steps, of basic steps where you do a little bit of computation, some small circuit, and then you look up some location in the big input Y, the server's input Y, you get it on the next step, you do some computation, look up the next location. That's what RAM computation looks like. And so the idea is, let's just use fully homomorphic encryption to do this. So we're going to encrypt the original input X with fully homomorphic encryption. That lets us evaluate circuits. We'll evaluate this basic CPU step circuit on it, and we'll get the encrypted state and the index that we need to look up the database. And now we somehow want to get a fully homomorphic encryption of the ith bit of the database, and we could feed it into the next step and continue. But how do we do this? We have an encryption of an index I, and we want to get the ith bit of the database. If we had a peer query, a doubly efficient peer query for I, we could do this, but we don't. We have a fully homomorphic encryption I for I. There's a mismatch. This is not itself a doubly efficient peer query for I. But it turns out, so the main challenge is, how do we kind of do this step? If we had a doubly efficient peer query for I, we could do it, but we don't quite have that. And it turns out that luckily for the schemes we have, we can make this work because we can actually easily convert FHE ciphertext into DEPIR queries, because DEPIR queries themselves are some sort of homomorphic ciphertext. So this is not generic. This is specific to this scheme. So I'm going to skip the details, but essentially, there's a nice way to convert back and forth. The peer queries are themselves some sort of homomorphic encryption, this algebraic, somewhat homomorphic encryption. And there's a nice way to convert between these FHE ciphertexts that you get from the computation into these queries and back. So I'll ignore the details. I think I'm running out of time, so I want to kind of wrap up. So this just gives you computation that doesn't have random access to X and doesn't do writes to Y, but you can easily get random access to X similarly by using DEPIR on X as well on the client's input. And you can allow writes by using the updatable DEPIR data structure. So yeah, let me wrap up. So in conclusion, we managed to construct this doubly efficient peer and FHE params from the ring LW assumption. There's a lot of good open questions. Maybe the one real interesting one is, can we do it from plain learning with errors assumption? Almost everything else in cryptography that we can do from ring LW, we can also do from plain LW. Sometimes it takes a little longer to figure it out, but it worked. For everything else, we managed to do it. So this is the only problem at this point where I don't know how to do that. It's a great open question whether it can be done. Practical efficiency is a huge open question. Right now, it's really highly impractical. And last, there's a lot of obvious application. Anywhere where you were going to use polymorphic encryption, now use RAM-FHE and maybe get the RAM savings. But there were a lot of non-obvious applications of FHE. It ended up having lots of other cool implications, surprising implications, lots of areas of cryptography. Can we find other less obvious applications of this type of FHE? And we have a recent paper crypto that does that found some such applications, but I think there's a lot of room for more. So let me end here.